My name is Tom Giovanetti. I'm the president of the Institute for Policy Innovation, and we're delighted that you're with us today. The Institute for Policy Innovation is a 35-year-old free market think tank based in Dallas, Texas. We work mostly on issues that are related to economic growth and human flourishing. I'd like to welcome you all to our Zoom policy briefing today with Dr. Matthew Wielicki on the truth about atmospheric carbon dioxide. Thanks for joining us. We'd appreciate you all being with us. I want to especially thank those of you who are financial supporters of IPI for joining us today. You make this possible. We deeply appreciate your support of IPI. After this discussion, if you decide that you would like to become a supporter of IPI, we would, of course, love that and welcome that. And our Director of Events and Development, Addie Crimmins, would be delighted to speak with you about how you can be a supporter of IPI. So please feel free to contact Addie. She would love to recruit you as a member of IPI's Giving Society. It's our Giving Society that makes these kinds of events possible. And so we need as many partners as possible. So if you've not partnered with us up to this point, we would love to have you as a partner for our work. And so Addie Crimmins is the person you want to talk to about that. We have a lot of participants today, which is great. I want to make a point of saying that we will allow for a Q&A portion of the program, but we will use the raise hand function in Zoom for Q&A. We will not monitor the chat. You're welcome to participate in the chat if you like to, but we will not be monitoring the chat for questions. We'll be using the raise hand function for questions. So if you have a question or a point or an argument that you want to make, please use the raised hand function for doing that. If you look down at the bottom of your Zoom window, you'll see a menu option that says raise hand, and that's how you can register your question, your comment, your objection, whatever you would like to say. And we will be monitoring that. This event will also be recorded and it will be made available on our website and on our YouTube channel. So if you enjoy this and you want to share it with people, you'll be able to do that. You'll be able to share it from YouTube and you'll be able to share it from IPI's website. I want to sort of address the sort of big climate change argument that goes on in the policy world. We at the Institute for Policy Innovation are not afraid of science. We're not afraid of facts. In fact, we make our living on facts and science. That's what we specialize in. We go where the facts lead us, and we go where our public policy philosophy leads us. So that means that we are not climate change deniers. We're not science deniers. No one on the program today is a science denier or a climate change denier. It's pretty clear, if you know anything about Earth's history, that the climate on Earth is always changing, as is the climate on Mars and other planets. The real questions we need to be asking is climate change a problem? Is it a bad thing? Is it due to human activity? And is there anything within reason that we can do about it where the solution is not worse than the problem? I think today's discussion is going to have a lot to do with the first couple of questions that I asked. Is climate change a problem? Is it a bad thing? When the glaciers melt away, is that the climate crisis? Or was the climate crisis when the glacier first showed up in the first place? And at this point, it's probably best for me to bow out and leave the discussion to the experts. So leading the discussion today will be IPI's resident scholar, Dr. Merrill Matthews. IPI's board chairman, Wayne Stoltenberg, will also be participating. And with that, I will turn things over to the experts, beginning with Dr. Merrill Matthews. Dr. Matthews, please take over the program.
All right, and I'm going to introduce our speaker, Earth Science Professor Matthew Wielicki. He's an expert in atmospheric CO2, carbon dioxide, and the role it plays in our planet's ecology. He was formerly at the University of Alabama, but he recently left because of issues, a variety of reasons, issues going around a lot of universities right now. He was also a postdoctoral research scientist in the Department of Earth, Planetary, and Science and Space Sciences at the Institute of Planets and Exoplanets at the University of California in Los Angeles. And so, Doctor, I'm going to turn it over to you and let you take it.
All right. Thank you, Dr. Matthews. Thank you guys for having me. Thank you for the invitation. I agree with a lot of, I've been looking onto the Institute's website, and I definitely share a lot of the concerns. I think that climate has become, as we were just talking about with Tom before we started, a tool that essentially is becoming something that is a tool for the government to control a lot of our decisions in our everyday lives. And so I just wanted to give you kind of my roundabout story of how I kind of entered into climate science. I wasn't per se a climate science researcher at the beginning, but I ended up doing a lot of work in just kind of being a climate science communicator and trying to expose people to some of the science that maybe the mainstream media misses. And it became very apparent to me that that was enough to essentially leave my position in academia, or essentially be slightly pushed out. So I was just going to give you my roundabout journey of how that happened, and tell you a little bit about what I think the geologic evidence suggests about the role that atmospheric concentrations of greenhouse gases, particularly CO2, plays in global surface temperatures. And I'm going to primarily talk about the Northern Hemisphere because that's where 90% of the world's population lives. To correct Dr. Matthews a little bit, I'm just going to share my screen real quick. So I was originally a isotope geochemist. I'm still an isotope geochemist. And my PhD and most of my work was outside of climate science. It was primarily in isotope geochemistry in terms of figuring out the age of certain layers of rocks. And that's what you see here in that lower left corner. That's a little zircon crystal, and that is what we would use to date certain layers. And we would work with climate scientists and folks working in the climate fields, and they would want to figure out what was the age of a certain layer of rock, and that's what we would essentially do. But I did my best to essentially stay out of the climate sciences because it was already becoming rather political as I was in graduate school. I noticed that because very quickly, I noticed that the definition of climate science changed. I mean, of climate change changed. In fact, climate change used to be the first 8 words you see there, a change in global or regional climate patterns. And that was the definition of climate change until somewhere around the late 2000s. And then there was something added on, in particular, a change apparent from the mid to late 20th century onwards and attributed largely to the increased levels of atmospheric carbon dioxide produced by the use of fossil fuels. That's not the definition of climate change. That would be like looking up the definition of lung cancer and reading that lung cancer is a cancer of the lungs produced by the tobacco industry. And so it was clear to me that this was a science that was being influenced pretty dramatically by outside factors. As a graduate student, it was clear I didn't really want to get involved. I worked with climate scientists, and I published papers and with climate implications, but I tried to really stay out of the debate. At this point, it was more of self-preservation. I wasn't really interested in getting involved. It already seemed rather heated at that time. And it was clear to me, though, that when people said climate change, what they really meant was this. They meant anthropogenic global warming, right? And that's a theory that tries to explain a trend in warming since essentially the Industrial Revolution till today and attribute that warming to the anthropogenic emissions of CO2. That's what they mean when they mean climate change. That's not what climate change really means, but that's essentially what the term has become. And so it was clear that there was a lot of outside influence that was really driving this science. And so I was already becoming concerned. And I didn't want to rock the boat, as most or scientists are in the industry. You hear about this consensus that's absolutely absurd. There's absolutely no consensus. What there is a consensus about is that if you speak up about this stuff right now, you may put your job on the line. And I'll explain a little bit more about that because I experienced that directly. But it was clear that, you know, I wasn't going to really say anything, even though I was a little uncomfortable. And I have no real problems with CO2's role in the atmosphere. So this is just a quick reminder of how CO2 interacts with incoming solar radiation and outgoing radiation on the Earth. And really, we just want to focus here on the right-hand side. And what you see on this plot is wavelength at the bottom on the x-axis. That goes out to about 70 microns. That's about the width of a human hair. And that goes all the way down to about 0.2. So that's about the range of the incoming radiation. Now notice the incoming radiation tends to be focused on the shorter end of that, the shorter end of those wavelengths. You can see the visible spectrum here. And as we move down in this plot, we can see what the greenhouse gases in the atmosphere are essentially doing. And there's 5 predominant greenhouse gases: water vapor, carbon dioxide, oxygen, and ozone, which we'll assume is just one. That's O2 and O3, and methane and nitrous oxide. And so this just shows how that incoming solar radiation, which the atmosphere is relatively transparent to, you can see that here in the middle box, the gray bars, the total absorption and scattering. In the terms of the incoming radiation, the red, it's relatively transparent. Not much of that is being actually absorbed. What you can see is that some of it over here is being absorbed on the higher energy side, the lower wavelength. That's the bluer side, right? So if we think about Roy G. Biv, our spectrum of colors, that exists right here in the visible spectrum going from right to left. So you have red, orange, yellow, green, blue, indigo, violet. And then you can notice that on the left-hand side, you have more of this absorption going on. That's going on because of Rayleigh scattering. That's really complicated. We don't have to get into it, but it's just the interaction of the wavelengths with droplets in the air. That's why the sky is blue, because we can see that there is more absorption on the left-hand side of the visible spectrum. That's the blue, the high energy side of the spectrum. And so that's why the sky is blue. But this also shows us why, when the surface of the Earth heats up, and as it heats up, it releases energy back into space through thermal outgoing radiation in the infrared. And that's the purple that we see on the right-hand side. And that's essentially what the greenhouse gases in the atmosphere are trapping. They're trapping that infrared radiation. You may have experienced that before if you've been in, for example, a hot city or a hot area. I grew up in Fresno. Some of you in Texas may have experienced this on a hot summer day. If you have all your windows up in your car and you get into your car, it's really hot in there. It's even hotter than it was from the outside, right? That's the thermal, the visible spectrum coming in, heating up the interior of the car trying to release the thermal heat in the infrared, but because all the windows are up, it essentially gets trapped inside the car, and you might have to vent your car for a minute or two. That's essentially the greenhouse effect. But one thing that we can notice is that, for example, carbon dioxide has a much smaller role than water vapor. You can see that water vapor is by far the predominant greenhouse gas. Furthermore, methane, that we hear more and more about, especially in recent times, most of the methane absorption windows are completely already saturated by water vapor. And so you cannot absorb any more energy in those wavelengths because water vapor is already absorbing all of that energy. There is a small bump on the left-hand side in methane. That is essentially methane's contribution. This is one of the reasons I would argue that methane's warming potential that we hear about a lot in the mainstream media is a little bit overblown, or maybe a lot overblown. But essentially, I agreed with most of this. And I realized that, okay, CO2 has some effect. I clearly realized that there was outside influence and there was a lot of hyperbole in the science. But again, I was just finishing my PhD. I didn't really want to rock the boat. And then things changed. We were blessed with 2 baby boys. I started thinking a lot about a different type of future. I started thinking about not only what is the implications of climate change in terms of how much notoriety does it bring to my science? There's a lot of self-preservation instinct in earth scientists. Even though there's plenty in the field that have questions and really don't agree with a lot of it, they see it as essentially a noble lie, because what's the bad that can happen? It's going to just help us transition away from energies that they consider dirty to energies they consider clean, because they don't really understand how a lot of these are produced. But they think, what's the harm? And I got to admit, I was kind of in that boat at a time as well. But I think probably a lot of you that have children obviously know, when you have children, your perspective changes a little bit. You start to think a lot differently about the future. And so I started to think, what are the mental health aspects of telling young people that the climate is in crisis and in an emergency? And I started to notice that even at the picture here, when my son is only about 3 and we're starting to really introduce him to some of his first books, there's books already that would implicate humans as essentially bad for the planet, and the planet would be better off if there were less humans on the planet. And that made me very nervous in a way that I never really realized before. And so I started to look up studies like this. So this is a study that was in Nature not that long ago, 2019 or so. This was a survey of 10,000 young people, and you can see that over or close to 60% of them feel extremely worried or very worried about climate change. If they think about what words come to mind, how climate change makes them feel, they think about sad and afraid, anxious, angry, powerless, guilty. We were having a terrible impact on the mental health of young people. And so I started to really become a little bit more vocal about whether or not the science really supports the possible negative outcomes, especially in terms of mental health for young people. And then things changed again. And in 2020, end of 2019 and 2020, with the combination of things like the racial reckoning that was going on in the US, the ratcheting up of all of the climate, the verbiage that was used. There was no more talk of global warming or climate change. It was climate crisis, climate emergency, climate breakdown. Scientists were chaining themselves to banks. Obviously, COVID on top of all of this was adding to this. I started to realize that there was a problem in a lot of our institutions, and especially, and something that was really infiltrating into academia. And academia changed dramatically. Maybe I was blind to it before, and I've talked to lots of folks that say that, this stuff was here, and it just wasn't as pronounced in the STEM fields. In the STEM, we were really pretty immune still to a lot of the DEI things and stuff like that. We were really merit focused, engineering, the sciences, mathematics. I mean, it's hard to put that in because you have formulas and equations. And so we're still very merit focused. But in 2020, things radically changed. And everything in the university setting started to be framed through a lens of essentially race and what I think are unmutable characteristics. I can help you learn and I can teach you things, but I cannot change the amount of melanin in your skin. And so I can't make decisions about your role in our school and our program based on something that I can't change or affect. And when I started to speak out about that, it became very clear to me that this was essentially career suicide. I was tagged and basically connected to anti-Semitic writings that happened a few days later on campus that were completely unaffiliated by faculty members in the university. The university came and asked the faculty members in my department to no longer speak with me. My graduate students were harassed. It was clear that it was career suicide. These were things that you could not speak about. This was something that was untouchable. And in a university setting, and coming from, I'm originally born in communist Poland. Some of you that may have heard that discussion, but I think that maybe made my radar a little bit more sensitive to this illiberalism that I call it, the rise of illiberalism in academia. I was always attracted to the field because of the free exchange of ideas, and the way that we could battle with our minds is just a beautiful thing. And it leads us to progress, and it leads us to better answers. And so the fact that we couldn't discuss certain topics was really the nail in the coffin that made me decide to leave. We were far away from our families. Both my wife and I's family were California, and so being in Alabama at the time was difficult. But it was very clear that somebody needed to say something, and so I started to be a little bit more vocal. One thing that I started to do is I gave us a real simple 2-question survey to my students, and I was shocked by the answers. So I would ask them, have more people died in your lifetime due to climate-related disasters than your parents' lifetimes? And do climate-related disasters cost more today than your parents were your age? And I asked them to rate their answer on a scale of 1 to 5 on how confident they were in their answer. And it's great now with technology, they can do this on their cell phones, and we get instant replies right on the screen. It was great. And I was shocked. Everybody, essentially, vast majority, over 85%, said that significantly more people were losing their lives in climate-related disasters, and they were really confident in their answer. And they were also really confident that climate-related disasters were costing governments and civilians and societies more today than ever before. And they were also very confident. And as someone in the earth sciences, our whole goal is to teach people the state of the climate and the state of the planet, and give them the right idea of how the planet is the actual state of climate and how it's influencing human society. And we were giving them the exact upside down message. Somehow the students were convinced of the exact opposite things, and they were confident in their answers. The facts are that fewer people die today than ever before from climate-related disasters. That's the image on the left. And if we normalize our expenditures on things like weather losses and climate-related losses, and we normalize those to GDP, you could see that globally, there's essentially been a decrease. Now, a lot of times I'll show this picture and people say, whoa, wait a minute. I've seen a plot from NOAA that shows me that weather is costing more and more every year. And in fact, there are billion-dollar disasters that are occurring regularly all the time. And that's true. This is NOAA's graph right here. The most updated one I could find was from January this year for some reason. I checked today. And as you can see that there is a growth in the number of events that cost in the billions. Why is that? Well, this is CPI adjusted. So this is Consumer Price Index adjusted. So essentially they're trying to adjust for inflation. But what CPI adjustment doesn't account for is it doesn't account for things like transfer of populations and transfers of wealth. And if you think about places like Florida, for example, there has been a significant growth in both population and wealth since 1980 in Florida. And thus a hurricane that is the exact same strength comes in 1980 and 2023, the damage costs would be dramatically different. And NOAA freely admits this. In fact, they published a paper in 2013 that stated it is difficult to attribute any part of the trends in losses to climate variations or change, especially in the case of billion-dollar disasters. So my students had both the wrong idea of how many people were losing their lives during climate change and essentially how much it was costing. The two metrics that I would essentially use if I was going to somehow ascribe something an emergency or a crisis. That seems like two reasonable metrics. And so I would start to talk to my students and ask them, and we would always come back to the same question. Well, it's the CO2. We saw that the CO2 is so high now, and that's a concern. And obviously this is a crisis. And they would refer to this plot, right? This is a famous plot that we've seen probably from Al Gore at one time. This is a plot of the CO2 concentration in the ice cores from Antarctica. This is a few different ice cores from Antarctica. put together. And what you see here is over the last 800,000 years or so, the CO2 has fluctuated dramatically, anywhere from about 150, 165 or so, all the way up to about 300, but has never been above about 300. Well, a few questions come to mind when I see this. So the current level you can see there, I think it's 423-ish or so, 420, yeah, 3-ish, I think at the moment. A few questions come to mind. So are ice cores the best estimates for global CO2? Well, let's think about how ice forms. In Antarctica, so Antarctica is a desert. A lot of people think that a desert is strictly going to have a temperature profile to it, meaning it's going to be hot. But really, in our science, we ascribe or we attribute a desert area or an arid landscape to the amount of precipitation. And so it's really a function of how much precipitation falls in a certain region. And in a lot of parts of Antarctica, we would consider that a desert. It's actually very analogous to Mars, which is very cold because it's one planet farther away, and also very dry. So if you want to test some Mars rovers or Mars instruments, one of the ways they do that is they actually go to the dry valleys in Antarctica to test some of their equipment, because it's one of the closest places we can get to this kind of dry desert environment, very cold environment of Mars. But in order to form glacial ice, what you need is you need snowfall. And because that snowfall creates a overburden pressure as the snow piles up on top. And that overburden pressure is eventually what squeezes the bubbles out and isolates little bubbles, and thus locks in these little bubbles into the glacial ice and preserves them for thousands of years. And you can see in this image that sometimes that takes on the order of thousands of years. And so maybe Antarctica isn't the best place to look and compare modern measurements to from places like the Mauna Loa Observatory. Let's maybe think about other places we can look. So here's an example of some Antarctica ice cores compared to Greenland ice cores. They are using different proxies. We won't get into that. Some are the upper data set there is using hydrogen isotopes. The lower data set is using oxygen isotopes. But essentially, they're both trying to monitor the temperature change through time. The higher up the temperature, the warmer it is, the lower the temperature, the cooler it is. And so you can see that there's quite a bit of oscillations. And it appears that in Greenland, the oscillations are significantly bigger. Although they match up sometimes they don't. And there is a clear, much amplified signal in Greenland, so the Greenland being in the northern hemisphere, than in, for example, Antarctica. And remember, where do we put the measurements for our modern day measurements to splice on to our Antarctica ice cores? We put those in Mauna Loa. Those are on the big island of Hawaii. So that's the data set that you see spliced on to the end of the original NASA plot, or the one that you may see in Inconvenient Truth. And so that's already should be a red flag, because we know that the southern hemisphere has much smaller variations in both CO2 and temperature than the northern hemisphere. So we shouldn't be splicing on data sets from the northern hemisphere onto data sets from the southern hemisphere, and then claiming that the change is something that we should take note of, because the two data sets shouldn't actually be aligned. So what else can we look at? Well, there's a few other things that record CO2. Ice cores aren't the only thing that records CO2. And so let's look at a few other proxies. So here we have age on the x-axis. So from present day all the way back 4 million years. And we have CO2. So remember, we're somewhere about 422, 3 parts per million today. Well, something should jump out at you. It appears that within the last million years, CO2 has definitely been above 300 ppm in some places. So now this is a data set what we call paleosols. So these are ancient soils. These ancient soils will actually have a record of the past CO2. They're not isolated to just obviously the pole, Antarctica or Greenland. So these come from a whole bunch of different places. The different colors indicate different geographical locations. And you can see that it appears that there's more variation than possibly we were seeing in the ice cores. And maybe that makes sense if we think about, again, how glacial ice is forming. If glacial ice is taking this long amount of time to form, particularly in Antarctica, then it should make sense that it's going to be relatively insensitive to the short-term variations. It will still pick up the longer-term signals, but it won't be very sensitive to the short-term variation. Another way that we can look at past atmospheric CO2 is by looking at what we call plant stomata. So plants have little breathing holes, and these little breathing holes on plants, their density is directly proportional to the amount of CO2. And the amount of CO2, so if you have a high amount of atmospheric CO2, the plant won't take energy to create a lot of these little stomata because it can take in the enough CO2 through fewer amount of these on their leaf. And obviously it takes energy to create these extra cells and these extra structures. If the atmospheric CO2 is low, you have the exact opposite. And so when we look at plant stomata, for example, and we overlay that onto, again, the Antarctica CO2 data, what we see is that, again, plant stomata would suggest that there has been much more natural variation in atmospheric CO2 than maybe the ice cores in Antarctica are indicating. And so you can see that although, again, we're not getting up to the levels that we see today, we're not getting up to 423. So I think it's still pretty clear that humans are adding CO2 into the atmosphere. But I think it's disingenuous to claim that the measurement today from some baseline of Antarctic CO2 can all be attributed to anthropogenic emissions, because we can see here in this data set that plant stomata, in especially during these big climatic events, like, for example, the Younger Dryas, you have huge changes of on the order of 100 ppm in the matter of decades. And remember, we've had on the order of about 150 ppm since the start of the Industrial Revolution. But this is just a completely natural influence in the Northern Hemisphere. So this is from a data set in the Northern Hemisphere where this is completely a natural variation. And so we have to understand what data sets we're looking at, how we're adding modern measurements onto past measurements. But ultimately, I think that the CO2 story doesn't really hold up when you start to look at other proxies besides atmospheric CO2. So why do we care about CO2? CO2 isn't temperature. Well, CO2 and temperature appear to correlate when we look at the ice cores from Antarctica. And so this is a data set of the CO2 concentrations that we looked at before, and the oxygen isotope proxy temperature in the red. So we can't measure the temperature of the bubbles of ice because obviously they're just going to be the temperature of the ice. But we can look at the isotopes of oxygen inside the bubbles of ice, and that can be used as a proxy for temperature. And so the argument follows that, well, as CO2 goes up, temperature goes up. Okay, fair enough, but correlation and causation are very different things. So I took the time and drew some lines at the very lowest inflection point of the lower red lines, the dips in the lower red. One thing that you can see is in the first and the third and the fourth and the fifth glaciations, these are each glaciation cycles as we dip in and out, that the temperature starts to increase prior to the CO2 increasing. So is this correlation or is this causation? There's been multiple reports about this lag of CO2 and the fact that in the prior record, what we see is that temperature starts to increase, and then a few centuries later, the CO2 starts to increase. We have lots of good physical explanations for that, primarily Henry's law. That's a physical principle that suggests that as water warms, that it can hold less gas. You've probably experienced that. If you've cracked a soda on a hot day, it will go flat a lot quicker than if you cracked it out when you're skiing up here in Colorado for a day. And that's So that's the release of CO2 in the oceans as the planet heats up. As the planet heats up, the oceans kind of lag behind because they take a lot of energy before they actually change temperature. That's the thermal capacity of the water in the oceans. But as they do eventually warm up, they start to release CO2. And so we see this correlation of temperature and CO2. And correlation and causation are important. And we really need to make sure that people realize that they're very important distinctions, unless we're going to attribute, U.S. postal charges to global warming, or perhaps the per capita cheese consumption for people dying in tangled sheets. So it's really important to understand correlation and causation. So one thing that I always thought about was, okay, well, 800,000 years seems like a long time. But as somebody that studied early Earth and thinks about the last 4.5 billion years, I realized that 800,000 years is only about 0.02% of Earth's history. And so let's think about other times in Earth's history and how has CO2 and temperature correlated? Because if CO2 is really a causal factor, then every time CO2 is high, we should see warm temperatures because they should cause those warm temperatures. And what I started to look at what I like to focus on is the Phanerozoic. So that's what you're looking at here. That's the last 550 million years. This is the time period where living organisms developed hard parts, teeth, bones, shells. So we have a really good fossil record. Obviously, it gets better the closer to present day you get. But we have a better idea of the last 550 million years or so than we do of deep time, billions of years ago. So I try to focus on the last 550 million years. And what you can see here is that the level of CO2 today at 420 parts per million is very low on this plot. In fact, we're one of the lower levels that we've been in a long time, and by far, one of the lowest for the last 550 million years. And so how does CO2 correlate to surface temperature as we go back in time? Well, one of the ways to look at that is let's think about the glaciations. It's difficult for us to really know what's happening in the global environment unless we get into something like a glacial period. A glacial period really leaves a lot of evidence behind. It scours rock away. It leaves geologic evidence in the form of moraines, which are these deposits that we can date. And so we really have good evidence of when we had glacial periods. And if we think about when we had glacial periods, and then we compare that to the amount of CO2, so what we're looking at here is the pressure of CO2 at the time at this time down here, and versus the pressure of CO2 today. And so this would be 2 times more, and 3 times more, and 4 times more, and 5 times more. And one thing that sticks out to me in this plot, and in the upper portion of this plot, in the gray bars on the upper portion, the gray shaded areas are time periods of glaciation. And the white boxes in between those gray boxes would be warmer periods. One thing that you can see is that it appears that glacial periods are correlated with high CO2 stands. So in the original one of the earliest glaciations that we have evidence for, this is the Andean-Saharan glaciation, or the End-Ordovician glaciation. This is a time period when CO2 levels were at least 3 times higher than today. And yet we still have a global glacial period. And so this was really evidence to me that the atmosphere is relatively insensitive to the atmospheric concentration of CO2. Now, the planet appears to have been getting hotter, though. This is a plot from NASA and NOAA and the Japanese Meteorological Agency, and then the UK office, of all of their climate measurements for global temperature anomaly. But what's global temperature anomaly really mean? Who lives at the global temperature? So this is a way that reduces a lot of complexity in the climate system to make it appear as though something's happening. And what they claim is that we are reaching temperatures because of this CO2 effect, this greenhouse effect, that we haven't had in the last 125,000 years. I think the Washington Post had a headline like this just a day or two ago. And they come back to this global surface temperature plot. And so, again, as someone that works in maybe more longer time frames or deeper time from my geologic background, and likes to think a little bit more regionally too. I don't understand how we can average the entire global temperature. First, we have elevation changes. Second, we have dramatically different temperatures in terms of latitude. There's very dramatic differences in land masses in the northern hemisphere and southern hemisphere. That has dramatic changes or implications on the temperature. So this is just a reductionist way. So let's think about how temperature has changed in the last 125,000 years, and let's look at some specific places. Well, first of all, the temperature, this growth in temperature isn't that apparent in the last 18 years in the US. So in the last 18 years, the US has updated its climate network. It's called the US Climate Reference Network because of a lot of problems with their old networks and the urban heat island effect. But you can see that over the last 18 years or so, since 2005, the US hasn't had dramatic warming. There's been warming. So this is a temperature anomaly plot. So that anything that if the average is above zero, there's been some subtle warming. But again, there's no trend in this data. And if we start to look regionally and we start to look around, for example, where I was born in Poland, we can see that in Poland, just a few thousand years ago, the temperatures were significantly warmer. And they were significantly warmer in Ethiopia a few thousand years ago. They were significantly warmer in the Ural Mountains a few thousand years ago. The sea levels were significantly higher in Qatar a few thousand years ago. Sea levels were significantly higher in Indonesia a few thousand years ago. And so if CO2 is driving temperature, and the Holocene, just 6,000 years ago, we have pre-industrial levels of atmospheric CO2, and so many places on the planet, predominantly in the northern hemisphere, I grant that, are significantly warmer. Should we really have a lot of expectation to a change in surface temperature if we change the anthropogenic emission side of the carbon cycle? And so a lot of these temperature profiles that I just showed you. I'm going a little fast now because I want to leave time for questions and discussion. I can come back to this, but a lot of the plots I showed you are reconstructions from a lot of different data sets. And so a lot of those attribute that heating back to what we call the Holocene thermal maximum. And so this is a time period that's been very inconvenient for the whole story of CO2 driving temperatures, because it appears that there was a lot of areas that were significantly warmer, even though we were at pre-industrial levels of CO2. Here's that example of those pre-industrial levels of CO2 during that Holocene. And so just two more things. There's been a lot of discussion about, well, it's not the amount of warmth and things like that. It's the rate of change. It's the rate of change we should be worried about. So this is the data set from the Greenland ice cores. This is 6 ice cores that have been put together to try to average out. The dark line on the far right is the modern measurements that have been spliced onto this, because again, ice takes a long time to form. So it's not picking up the changes over the last few decades. So usually in these types of plots, you'll see a darker line or some different color line at the end, which is the modern measurements. But notice that I've highlighted 6 times in this data set where the northern hemisphere temperatures have changed at the same rate they're changing today. And remember that we just looked at the CO2. There's no change in CO2 at these times. And so I have a real problem when the IPCC produces plots like you see in the lower left, where they claim that there is NAT, stands for natural variability, where they claim that there is no natural variability in the system. If there was no natural variability in the system, I would suspect that this line going back before the industrial age would have looked flat. And so this raises a lot of questions. This raises the questions of, well, how much of the change in pre-industrial level CO2 is actually anthropogenic, and how much of the temperature change is due to anthropogenic CO2, and how much is due to natural variation. And this becomes a real big issue, because we know this types of change happen in the past, and we shouldn't pretend that these types of changes won't happen again in the future, and ascribing them to an industry rather than an industry that, by the way, didn't exist for the 6 that I highlight, and trying to ascribe it to that as opposed to trying to understand it, I think puts us at a much riskier future than if we try to understand it. So just a couple take-home messages. The geologic record suggests that global surface temperatures, particularly in the northern hemisphere, I think that's important, are relatively insensitive to atmospheric greenhouse gases. Thus, we should have no reasonable expectation of a change in surface temperature to a reduction of anthropogenic greenhouse gas emissions. That's all I had for you guys, but that's kind of the take-home message there. One thing that I want to add is we should have every expectation of significant climatic changes. We know it, particularly in the northern hemisphere. And let me emphasize, 90% of the world's population live north of the equator. That's predominantly because that's where the land masses tend to be congregated. And so we will see significant changes. We have records of 6, 7, 8 degrees Celsius changes in decades in near the Arctic Circle. And we're talking about 1.1 degrees since 1880 as a climate crisis. And so we definitely should be preparing ourselves for these radical changes. And the best way, I think, to adapt and reduce the effect of such a change is to make sure that we have plenty of energy ready to go, because it's going to require a lot of infrastructure to be able to adapt to such changes. But anyway, that's kind of all I had. I'd love to discuss and take any questions. I'll stop sharing.
Well, thank you, Dr. Wielicki. I'm going to turn it over to Wayne to start us off on some questions.
Thank you, Merrill. I appreciate that. First, I'd like to thank Dr. Wielicki for that presentation, very enlightening. I'd also like to encourage our audience to consider subscribing to his Substack. I do best $8 I spend every month. I think that's about what it is. He has really good articles, and having the data in winning these arguments is really important, because with the data and a little bit of critical thinking, that's really all you need. You don't need a whole lot more. 2 quick questions for you, Dr. Wielicki. I'll give you the first one. One of the early slides that you showed talked about saturation. And what I took away from that is the amount of infrared radiation that CO2, I guess, can trap is pretty limited, given it seems to be trapping about as much as it can, and water vapor is picking up the rest. Have I got that right? And that would imply that increases in CO2 aren't linear in terms of additional radiation being trapped. Can you talk about that concept of saturation?
Yeah, so that's absolutely true. So saturation essentially means that, well, so saturation in the methane's implication means that there's essentially there's none of that wavelength escaping anyway. So adding methane can't trap anymore because none is escaping. But for what you're talking about in terms of the potential of every molecule of CO2 to trap heat, CO2's potential to trap heat is actually logarithmic. So it's not linear. So it essentially tapers very quickly as you get to higher and higher concentrations of CO2. And so there's a lot of debate about this, but we talk a lot about the potential of doubling CO2. What's the warming potential of doubling CO2? And you'll see estimates that range anywhere from, less than a degree to 4 degrees. And so it's all over the place, but it is true that the potential and the absorption potential, it's logarithmic. So it's decaying really quickly. So when you add a molecule at 300 ppm, it does way more than if you added it at 500 ppm. And so it will taper away. This is one of the reasons that the IPCC requires a lot of these feedback loops. You don't essentially get enough warming from the CO2 itself. The CO2, because we are already at 400, and as we go up to 600 or 700 or whatever, the peak would be what their estimates are. There's just not enough there. And so they employ a lot of these feedback mechanisms that amplifies that signal. And thus you can get to these very catastrophic events. But it's absolutely true that every molecule that we add, each one does a little bit less than the one we added previous.
Okay. And one other question for you. I really liked your graph that showed geologic time, i.e. the last 500 million years. And when you look at that, one would say, gosh, we're at a very low level of atmospheric CO2 concentration. And oh, by the way, zero CO2 would be catastrophic because life wouldn't exist, because CO2 is such a building block of life. And below 150 ppm, we really don't have plant life, so I don't think there'd be a lot of animal life either. So I guess when you look at 280 parts per million pre-industrial revolution, most of the increase we've seen has been after World War II. So, that's, call it 75 years, 140 parts per million. It's a little less than 2 parts per million a year increase, meaning to go from 400 to 800 would take another 200 years. And we as humans generally haven't used the same energy source for that long a period of time. So again, it's happening very slowly. And chances are, if we use nuclear or something else will come along we don't know about, it seems unlikely to be a huge problem, something you'd want to really destroy the economy with and radically increase energy costs throughout the globe, which is going to really disadvantage poor populations. Could you comment on that?
Yeah, see, everything is a trade-off. This is something that I think we have to understand. There's just no free energy. There's no free anything. And we have to figure out what the trade-offs we're willing to give, and what are the priorities that we want to put. And I had the blessing of spending some time in Somalia in Africa. I went to second grade in Mogadishu, actually, and I got to live there. And it was, I didn't realize it at the time, but it became apparent to me that the reason that there was so much poverty in that country was because there was a lack of energy. There was a lack of reliable, cheap energy to build the infrastructure required. Every night I would fall asleep to the sound of a generator that my neighbors had that would kick in because the power would go out nightly. As a kid, I didn't know. It was kind of a nice humming sound. But I look back and I think about that, and not a lot has changed. And we're essentially prioritizing a hypothetical situation based of some future climate that I don't think we really have a good handle of predicting. We're prioritizing that over the billions of people that would love to have access to some reliable energy so they could build some infrastructure and have some opportunities that we take for granted, to see young people in the Western world gluing themselves to things and desecrating art because they think they are victims of something, when there are so many people on this planet that would just love to have access to some energy. We take it such for granted that it's such a privilege, and I think the science is weak. And so the negative aspects of these types of policies, I think, greatly outweigh any possible future potential climate disaster. We haven't seen it yet. If numbers start to shoot up and everything radically changes, I will change my story. Absolutely. But you have to show me the evidence before we start to make radical changes, especially at the expense of the poorest people on the planet.
All right, I'm going to ask Tom. Tom, are you ready with questions yet? Or do you need a second?
So I'm here and we have a couple of questions. We have a question here about, we know that CO2 in earlier Earth's history was much heavier than it is today. And we know that that correlated with large plant growth and luxurious plant growth. Is it possible that higher levels of CO2 would actually contribute more toward human flourishing today?
They have so far. I think I think there's no doubt that there's been a net benefit from atmospheric CO2 because of the agricultural yields that we see. I mean, for the first time in history, we have actually decoupled land use from yield, from agricultural yield. That comes from a few things. That comes from CO2 fertilization. So that's the plants just get more CO2 out of the atmosphere so they could grow more. But it also comes from synthetic fertilizers, which we also primarily make from methane as the raw material, right, in the Haber-Bosch process. And so it's absolutely true that if you look at today's society, we have had a net benefit from the increased in atmospheric CO2. But that's because so far none of the catastrophic predictions have taken place. The oceans aren't boiling. We don't have billions of people migrating because places are uninhabitable. In fact, I wrote a piece the other day that these places that they were talking about were going to be uninhabitable have had like a 20 million person increase in the last decade or so, something like 50% growth in these. They were talking about areas in the Middle East and even in like Southwest in Arizona. So if the catastrophic predictions start to become true, we should address that. We should have this conversation again. But at the present day, it is without a doubt that there has been a net benefit from just the gain of cheap and reliable energy and from the release of CO2. Absolutely.
We have another question. Is it not true that we are still coming out of the last ice age? This is something that we hear, that part of the mechanism for the current level of global warming may simply be that we are still coming out of the last ice age.
Yeah, this is so, climate change is timescales. I can argue it's cooling. I'll show you 65 million years and the planet has cooled dramatically. I can say it's relatively stable. I'll show you, the US over the last 18 years. I can say it's warming. I could show you some urban areas that have grown very dramatically. So it's really a matter of timescales. I think that since the last glacial maximum, it's a pretty safe assumption just to say that the planet has relatively been warming since the last glacial maximum. That's about 18-ish thousand years ago when sea levels were very low. We've seen this dramatic rise. Things have been relatively stable for the last, in terms of sea level, for the last few thousand years, which has been a great benefit because we've been able to build coastal cities. But it's clear when we look at the geologic record that is not the norm. That is an exception, and we better start looking at that geologic record and being ready, because I don't see any way that we're going to control planetary processes like this.
So your answer to that question raises a question of mine, which is something that I tend to call the tyranny of the status quo. We know from archaeology that there are ancient port cities that are now like 35 miles inland. We can tell that we in Texas, for instance, understand that most of the state of Texas was once an inland sea. If you go back far enough in the geological record. And so would you address for just a moment this idea of the tyranny of the status quo? We assume that because Mount Fuji has been ice capped during our lifetimes that it's supposed to be ice capped, right? We assume because the Chamonix Glacier in Switzerland is there that it's supposed to be there. And the counter narrative, of course, is that the climate crisis was not when the glacier melts away. The climate crisis was when the glacier showed up, because as these glaciers and as this ice melts away, we find evidence of human civilization in these areas that was driven away because of the ice and because of the snow. So to what degree are we victims of the tyranny of the status quo when it comes to climate?
Yeah, I think a lot. I wrote a piece that asked, why are we protecting a climate that tried to kill us? And because there's a recent article in Science that the closest humans came to extinction was during a glacial period about 900,000 years ago, when there was something like 1,200 individuals left, breeding pairs left. I mean, very close to extinction. So it's only been the last 1 or 2 years that our climate system has oscillated between these glacial and interglacial periods. This has been one of the most unstable regimes that we have seen in the last 550 million years. If you go back just 2 million or 3 million years, you get out of this weird oscillation where people argue it's because CO2 was so low that the orbital forcing of the Milankovitch cycles, which is how far away the Earth is from the sun, the tilt of the axis, the wobble of the axis, all of these forces that were relatively muted when CO2 levels were a little bit higher, they became the dominant factors and they made this huge oscillation. And so it's crazy that we're trying to protect this climate that essentially is very unstable. And it's weird that we all agree that it's relatively unstable, but for some reason we don't want it to change again. And because there's a glacier there, it has to be there forever. That's not the conservation values that Teddy Roosevelt would have talked about. That's not letting nature take its course. That seems to be trying to put your finger on nature because for some reason you think these things are pretty to look at or something. And so now no longer can nature, take its course because you enjoy this. That seems to be the ones that are essentially trying to control the nature and trying to stop any sort of natural variability. To me is crazy. The planet's going to change and we need to embrace that and accept it and adapt to it, which we do very well. But dilly-dallying around about spending trillions of dollars in some future climate that we don't really know is going to happen, I think is just money poorly spent.
It's not unlike the issue in the West about the fact that wildfires are a naturally occurring phenomenon, right? And that, in fact, there are species of pines who require regular wildfires in order to germinate, for the seeds to germinate. And so humans step in and the humans say, we know better. And so we're going to try to prevent these fires, right? And essentially what we're doing is we are acting in a way that is contrary with the natural cycles and with natural climate.
Yeah, so many of our solutions are worse for the environment than not doing anything at all. But people hate that idea. Like, we have to do something. We can't just sit back and do nothing. And okay, we can do small things, but this idea, we're a victim of our own success. Fire suppression, we got really good at fire suppression, and we like forests, and so we didn't want to see them burned. Well, guess what that leads to? That leads to really much bigger fires and instability in terms of how much dead underbrush there is and things. And so, so many of the solutions tend to be worse, and this is one of the problems. If you inflate the problem, then the solutions become grander and bigger, and thus they have worse unforeseen consequences down the road. And that really worries me.
We have one other issue, and that is, we mentioned this in our description of the event, and that is this decision that has been made by federal regulators to treat carbon dioxide as a pollutant. Carbon dioxide is necessary for life. It's necessary for plant life, and because mammal life depends on plant life, it's necessary for mammal life, but yet the EPA and various federal regulators have decided to treat carbon dioxide as a pollutant. Can you address sort of scientifically why this is just a ridiculous approach for the EPA to take?
Yeah, it's absolutely counter to their original definition of a pollutant. So that's not to say that if you'd had an atmosphere of 100% CO2, it wouldn't be bad for the planet. Sure, but let's just think about the actual biological aspects of photosynthesis, for example. So photosynthesis is most efficient at about 1,200 parts per million. Well, we know that because a lot of greenhouses that grow a lot of our food, they pump CO2 into their greenhouses in order for them to increase the yields. And a lot of these greenhouses are using artificial lights, and so they want to maximize photosynthetic efficiency so they can not shine the lights as much because the cost is really in the electricity of the lights. And so there's been a lot of studies that have shown that about 1,100 parts per million is optimal for photosynthetic efficiency. Well, and we also know that because we have a time period in the planet known as the Carboniferous. This is where we have most of our coal. The coal comes from this time period known as the Carboniferous, and that's why it's named that, because it's such a carbon-rich layer. And the average atmospheric CO2 at that time was on the order of 1,400 parts per million. And that was the time period where we think plant life, coal is essentially the deposits of terrestrial swamps. That's a time period when there was so much photosynthesis and so much organic matter in these swamps that we have some of the richest coal deposits on the planet. So, we can start worrying about CO2 maybe in the few thousand parts per million level. But to say that an increase from 280 to 420 is going to be detrimental to plants is exactly the opposite of what the science says. And we see it in the evidence in terms of the yields. Look at the corn yields that the US just reported a week ago. I mean, through the roof.
Yeah, if you're a greenhouse person or a plant person or a tree person or even an aquarium person, a lot of times you are purposely trying to boost up the amount of CO2, right, that is available to the plants, because that is the maximum. That allows for the maximum efficiency. And again, we know from archaeology that plants used to grow much larger, much taller, the leaves were larger, et cetera, et cetera. Is there a reason for us to think that that would be a more ideal climate than the climate that we have today?
I don't think there's a reason to think that that would have a dramatic influence on the climate at all. We know that at 3 times the level of today, we could have we could go into a full glacial cycle. And so, it's just I think the connection between expecting a climate at some atmospheric level of CO2, the framing of the question is already incorrect, because it assumes that we would know what a climate state would be at some level of CO2. And the fact is, we don't. It could be super warm at 3 times the level. In the Carboniferous, it was really warm at that time, but we also had glaciations at that same level. And so it just, the level of CO2 will not dictate the climate that we should expect.
In wrapping things up, I just want to remind folks that sort of every once in a while we will see a story in the news about a new skeleton that has been exposed, or a new town that has been exposed, or a new human civilization has been exposed because of ice melting away, or because of a glacier that has receded, and all of a sudden we find evidence of human civilization. And so I think the real question is, why do maybe it's just in human nature that we have this idea that the way things are right now are the way things are always supposed to be, where there's clear evidence from science and archaeology that the way things are today is not how things used to be, right? There are areas of the planet today that are inhabitable, that were habitable in ancient human history. And so that ought to at least give us pause, and it ought to at least give us a point of sort of humility to not assume that just because that mountain has ice caps on it today is necessarily the way that's supposed to be. And that's one of my big takeaways from your research and from your comments. Let me ask you to just sort of make some closing comments, and then we will thank folks for joining us.
Yeah, so I mean, I think if you took a real holistic look at the human condition, the human condition is improving, and the human condition has been improving for the last couple centuries. And I think that's primarily due to our ability to harness reliable energy, and reliable energy is at the core of all of this. And so, we should never put human, suffering or allow humans to suffer such that we can, protect a hypothetical future climate state. We need our priorities. And I think the science has been really manipulated by a lot of policymakers, a lot of government institutions. And the more you kind of dig into it, the less anxiety you'll feel. I think the less nervous you'll feel about it. And it will become clear that this isn't an emergency or a crisis, but we should be ready for significant changes in the climate, no matter if we're what type of fuel we're using or energy we're using. Climate change will happen, and sometimes it will be relatively significant. And the best way to prepare for it is to admit that it's going to happen and be ready, as opposed to try to blame it on some industry and hope that it doesn't happen by changing policy.
That's terrific. How can folks can follow your work?
You know, I mostly it's on my Substack, Irrational Fear. You can go to irrationalfear.com. And you'd be able to link to that, and that's where most of my writing occurs. But I share a lot on Twitter as well.
Okay, so
irrationalfear.com. Yes, sir.
Very good. We appreciate you being with us today. We appreciate Wayne Stoltenberg bringing you to our attention. Thank you, Wayne. Appreciate that. Thank you, Dr. Matthews, for managing the discussion. And I want to invite folks to join our website at ipi.org. If you would like to see other content that we've produced, you will be able, within a day or two of this event, be able to see archived video of this event on our website, on our YouTube channel. If you'd like to know more about IPI, or if you'd like to become a donor, I would invite you again to go to IPI's website and contact Addie Crimmins, our Director of Development. Thanks so much for joining us. We appreciate it. Thank you, Dr. Wielicki. Thank you so much for your time. We wish you the best. And thank you for giving us a sensible, rational, scientific approach to this issue, which has been so absent so often from this discussion.
Thank you, guys.
Thank you for joining us. Have a great rest of your day. Thank you.